Okay, let's recap what we did last session. So last session, we learned about neural networks, and then we saw that it's a nonlinear generalization of multinomial logistic regression. So this was multinomial logistic regression up until this point. Then a neural network is gonna generalize that to not only have a single layer, but also have multiple layers. So our input is going to go through multiple nonlinearities, and it's going to give us the features at the end, and these features are going to go through a multinomial logistic regression, and then it's going to enable us to model complex functions and complex nonlinearities, nonlinear relationship in our data set, and enable us to do classification. Not only that, but we also learned how to use Keras and TensorFlow through the lens of one example in R. So yes, you can do deep learning in R. And this library, not only it has these dense layers, it's going to have convolutional layers, it's going to have recurrent neural networks, it's going to have LSTMs, it's going to have attention models, transformers, I mean, a whole zoo of layers that you can use to build your neural network. So you can use it for images, you can use it for text, you can use it for speech, data, you can use it for data on a graph, which are the sort of data that you're gonna see if you end up working in a company like Facebook, LinkedIn, etc. These are social networks. Or if you do genomics, you're gonna have these types of data on graphs. And all of them you can have access to through this Keras package. Okay, and we learned how to optimize our method, how to compile it against our metric and our loss function. And then the training takes a while, but once the training is done, the algorithm that you're going to use for your production is going to be very fast, and it's going to be very accurate also. And before deep learning, we had support vector machines. And the idea of a support vector machine is this. Let's say our task is classifying the points in this plane, and we have two classes, the red class and the blue class. And let's say you only have two classes for now. The question of generalizing this method to multiple classes is more advanced topics. So you're going to see that in your more advanced courses in data science and statistics and machine learning. But for now, let's assume you have two classes, the blue class, the red class. A support vector machine will try to separate this data using a line. And let's say this is your line. This is your decision boundary. Anything to the right of decision boundary is going to be classified as a blue class. Anything to the left of this line is going to get classified as the red class. Not only that, but you want to have some leeway for your decision boundary. So you want to have support, some support to the right of this, some support to the left of this when you want to do training, because once the training is done, some of your observations might fall here, and then this is going to be your decision boundary and still doing the correct prediction. Okay, that's why we are going to introduce two new lines. One is going to be the line, the first decision boundary is when you have 0 for your right hand side. Then this line here, that's defining some margin for you. That's going to be the line that's corresponding to 1. And the other line is going to be the one that corresponds to -1. And there is a margin between these two. This is your margin of error. Okay. Now there are a couple of questions here. What is this margin? What is the formula for that? And that's going to be using the formula between two lines, the distance between two lines. That's your first line. This is the second line. And the distance between these two lines is going to be 2, because you have a 1 here and -1 here. So it's going to be 2 divided by the norm of W. Basically, W is a vector, and it's going to be the L2 norm of that vector. And the norm, if we don't know what that is, if you have a scalar, the norm is going to correspond to the absolute value of that scalar. If you have a vector with two entries, let's say W1 and W2, the norm is going to be W1 squared plus W2 squared, and then the square root of that. It's a generalization of the absolute value for a scalar. If you have three numbers in your vector, W1, W2, and W3, it's going to be W1 squared plus W2 squared plus W3 squared, and then the square root of the entire thing. Okay, that's the norm. And this margin is going to be 2 divided by that norm. The idea is that you want to maximize this margin. That's the role of training. So you want to maximize this margin. So you are maximizing 2 over the norm of W. This is equivalent to minimizing the norm of W. Okay, that's the first part during training. And then there is another concept. Why do they call it support vector machines? It's about vectors. All of these observations are vectors. These are two-dimensional vectors. That's where the vector is coming from. And support are these support vectors. The ones, the training data that are falling right on top of this line and the one below, these are all being called support vectors. So this is a support vector, this is a support vector, this and this. Now you might say, okay, this data is easily classifiable. You can classify them by a line. What if there is a complicated relationship between this data? What if you have a complex decision boundary? And the way that usually people take care of that is they take this x and they push it through a function. So you take x and then you do a nonlinear function of x, and that's they call it kernel trick. So that's a trick that you make. And then the hope is that if this is two-dimensional and if your function is going to take you from something two-dimensional to a high-dimensional vector, then it's probably easier to classify complex relationship between data in higher dimensions compared to lower dimensions. So you have a function on top of phi. It could be phi of x. Phi is your function. Okay, using kernel trick, you can model complex relationship between your data. Rather than it being a line, it could be now a curve. So there are two concepts. One, you are maximizing this margin. The other one is you take x and you push it through a nonlinearity. And that's exactly what's going to happen. So this is going to give you an objective function that you want to minimize. In machine learning, you like to minimize. That's the convention. We want to minimize this norm of W squared. And as I said, the norm, if your W is W1, W2, L dots, W, let's say it's d-dimensional. So you have a d-dimensional vector. And then the norm of W is going to be W1 squared plus W2 squared plus L dots WD squared. So that's the norm of W. And actually it's the norm squared because that's what we are going to need. It's the norm squared. So the formula that you see here is just this. And there is a plus here. And this margin that you have up there, margin is 2 over the norm of W. So that's your margin. The margin is 2 over norm of W. 2 is coming from, this is 1, this is -1, that's going to give you 2. And then the norm of W is going to give you the distance between these two. Actually, the entire thing is the distance between these two lines. 2 over W. You want to maximize the margin, which is equivalent to minimizing this norm. It is equivalent to minimizing the norm squared. So that's what we want to do. At the same time, we have to penalize any observation that is being classified wrong. So if any observation is being classified, if any of these blue dots is falling to the left of our decision boundary during training, we want to penalize that. And that's for penalty. So let's see what that is doing. So we are gonna not penalize, we are gonna be happy if 1 minus yi, this term is yi, times W transpose xi plus b is less than or equal to 0. If this is less than or equal to 0, we are gonna be happy because the maximum of 0 and something negative is gonna be 0, and then we are not gonna penalize. this term is going to be 0, and then there is no gradients updating W and B. Okay, so we are going to be happy if this is negative. And yi is either a +1 or a -1. And let's say the +1 is going to correspond to this blue data. The label of the blue data is +1. The label of the red data is -1. So that's our yi. And I is each one of these data. So this is data 1, 2, 3, 4, and this is the ith data, for instance. And there is a corresponding xi to it. This is xi. The coordinates are going to give you xi. And xi is a two-dimensional vector in our example. And w is two-dimensional in this example. And b is one-dimensional. And yi is either a +1 or a -1. It's one-dimensional. So it's a scalar. This is a scalar. This is a two-dimensional vector. This is a two-dimensional vector. But in general, it could be d-dimensional. You could have d features. Now, why are we going to be happy if this is less than or equal to 0? Why am I claiming that? The reason is this. If yi is 1, so yi is either 1 or -1. Let's assume it is 1. So this is 1. Then you take all of these terms to the right-hand side, and that's going to give you W transpose xi plus b bigger than or equal to 1. If yi is 1, and these are all the blue data, we are going to be happy if they are on the right-hand side of this line. And all of these data points on the right-hand side of this line are the ones that are bigger than or equal to 1. Okay, this is exactly equal to 1. If it is bigger than or equal to 1, you're to the right of that line, and that's when you're going to be happy. You're classifying your data point correctly. And if you're happy, you're not going to penalize it. As soon as this becomes positive, this maximum is going to give you this value, and that's when you're going to penalize. You don't want that to happen, so your objective function is going to try to minimize that. It's going to try to minimize that mistake. So what does it mean? As soon as any of these blue ones, blue data, fall to the left of this line, they are going to be penalized. It means that you're going to adjust your W and B so that they don't fall to the left side of that line. So that's for the blue data. For the red data, yi is -1. Okay, they are being classified as red, and red is -1. For those ones, if you use this formula, you have yi is -1. It's going to become 1 plus W transpose xi plus b. And now you take this, you keep it to the same side. It's going to be W transpose xi plus b. And you take 1 to the right side. It's going to become -1. Okay. And then you're going to be happy if this is happening. If for any of your red data, you are to the left of this line, that data is being classified correctly. And if they are being classified correctly, you are happy. If one of these data fall to the right of this line, this objective function is going to become positive. This value is going to become positive, and then you're going to penalize that. You're going to try to adjust your weights and biases such that this doesn't happen. So that's the role of training. There are two cases, either yi is 1, either it is -1, and this objective function is trying to make sure that first, the distance, the margin between these two lines is as wide as possible, and at the same time, you want to keep your data in the correct, you want them to be classified correctly. So increase the margin, and at the same time, try to make the classifier predict the classes correctly, okay, and penalize it if there is any mistakes. So is everything clear? Are there any questions? So you can use support vector machines to do classification between two classes. Now the question is, what happens when you have multiple classes? That's going to be more work. It's not going to be as easy. There is actually a fast solution to that. That's called classifying one versus the rest. So you're going to hear that a lot also. If you have a classifier that's able to classify between two classes, you can use that to do multi-class classification. That's called one versus rest. You first classify one class, and then you lump everything else together in another class. You classify between them, and then you do that for all of your classes, and in the end you vote what class it should be. Okay, There is actually a way to do support vector in machines for multiple classes, but that's more advanced topic. Uh, we talked about this x being a nonlinear function. It doesn't have to be x, it could be any nonlinear function. And then you are going to be able to model curves here rather than simple lines. We talked about that. And I guess we are good to take a look at the code or what package we need to use. So the function is going to be called SVM. We are going to use, oh, one other thing that I forgot to say, you can use support vector machines to do regression as well. You're going to have a soft margin and then you can do regression. So support vector machines, you can use them for regression and classification at the same time. Now we are going to call that function. We are going to classify cut versus all of the rest of the variables. We are using the diamonds data to define the model. So at the same time, it's fitting. It's taking longer because one issue that support vector machines have is that their computational cost is the size of your data cubed. So the bigger is the size of your data, the longer your algorithm is going to take to converge, because you're going to have to invert some matrices that have the size of your data. And these are usually full matrices. By full, I mean all of the entries in the matrix are non-zero. They are not sparse. And that's going to take the computational cost is going to be the number of data cubed to the power 3. So the bigger your data, the longer it's going to take. And we know that our data is big. This one is relatively big. Let's take a look at our model, and let's take a look at the dimension of our training data. There are 37,000 data points in this data. They have 8 dimensions. 23,000 of them are falling on these two boundaries. They are support vectors. And our boundary is probably a nonlinear function. Yes, so it's using a kernel and it's using a radial kernel. So it's using a nonlinear function on top of x. So that's our model. Let's take a look at our prediction. Again, prediction is also going to take some time because this one also scales with the number of data in this test data. And then the confusion matrix. It's actually not a bad algorithm if you think about it, and it's 75% accurate. Okay, any questions so far? So the point here is not to teach you the math behind these methods. The idea here is to teach you how to use them, what package you need to use, and how do you apply, how do you call that on your data, and try to interpret your method a little bit. Why is it taking longer than what I'm used to seeing in other methods? Why is it slower? What are the advantages? What are the disadvantages of this method versus the other one? And in the end, try to analyze your data and explore your data using these methods. Okay? Any questions before I move to decision trees?